Hopefully you came up with an expression for the acceleration, I should say the centripetal acceleration, that looks something like this, where you take the speed, you square it, and you divide by r. And if you look at this, speed squared is meters squared per second squared, divided by r, which is units of meters, will give you units of meters per second squared for the centripetal acceleration, which is what it should be because it's like any other acceleration. It has units of meters per second squared. Let's go ahead and think a little bit more about what this v means. Imagine you're standing on the Earth at the equator. The radius of the Earth at the equator is about 6,400 kilometers. Now consider how fast you're moving. In one day, 24 hours, you turn around the Earth once. All right, so you go around, the Earth spins once in 24 hours. So let's figure out how fast you had to have been moving. Well, if your radius is 6,400 kilometers, in meters, that's 6,400,000 meters. The circumference of the Earth in meters would be 2 pi times that number. If you divide that by the time it takes you to go around once, that's 24 hours, and each hour is 3,600 seconds. This is just a conversion right here. The result will be that somebody at the equator is moving at 465 meters per second, which is almost double the speed of sound, which is pretty impressive. You wouldn't know that if you're just at the equator. And we'll look at that, what the implications of that are in a little bit, but I thought it would be useful for us to think a little bit about what speed is for an object moving in a circular path. And in this case, the object is somebody standing at the equator, anywhere on the Earth. Some applications of circular motion get kind of interesting. One of them is the roller coaster. Many of you have probably ridden on a roller coaster at some point in your life. And what's interesting about a roller coaster, and this is a great physics demo for those of you who are still working on getting your demos together, when the roller coaster is upside down here, which is what the next slide shows, it's like that for an instant of time. The roller coaster is upside down, yet it doesn't seem to fall, but it continues to roll down and then leave. What's actually going on there? We can think a little bit about circular motion to come up with what is the mechanism for how this manages to take place. One thing which is worth trying is try running your roller coaster but doing it slowly. And if you go too slowly, you'll find it goes up to a certain distance and then comes back down. Maybe a little faster, it'll go up to here and it'll kind of fall a bit. If you go a bit faster, it'll go up to here and then fall from there. If you go just past a certain cutoff or threshold, you'll find that the roller coaster will come up here, it won't fall, it'll make it across here. But you have to be going fast enough for that to take place. And so I thought it would be interesting for us to look at that, as well as to look conceptually at what's going on. It's funny how if it goes too slowly, you won't make it. If you go fast enough, you will. So caution of going slow isn't always the best thing to consider when trying to do something that seems a little dicey, like going upside down on a roller coaster. You don't want to take that slow. If you take it slow, you're going to fall. You actually have to go as fast as you can. And you might notice, those of you who do things like skateboard or surf, you might have experienced something like that, where you actually have to go a certain speed. You don't want to hesitate in order to try to make something happen, some sort of a special jump or something you're trying to do. It's the same idea here with a roller coaster. So the other thing that's interesting is as this cart is going this way, what is actually happening is it is falling. You can think about it like this. This cart's rolling up here, and it's falling. But it's falling such that as it's falling, it's also moving this way. So as it's falling, it's remaining in contact with the track. So you can think that word contact is important. It's actually the normal force or contact force which keeps the roller coaster on the track as it goes around the loop. And I'm going to move on to another video. I'm going to stop this video, but I'm going to end this video by asking you to do this. See if you can sketch what forces are acting on the cart when it is upside down on the roller coaster. First of all, think about how many forces there are. Ignore friction in this case. And then sketch their direction and name them when the roller coaster is upside down on the track like it is here. And we'll begin the next video thinking about that problem.